Your Majesty, ladies and gentlemen, it's a great honor for me to be able to speak about science in front of such a distinguished audience. I must apologize not to be able to speak in Spanish, so I'll have to speak in English, which is, after all, the language of science today. I will be talking to you about quantum physics. In fact, we are celebrating this year the 100th anniversary of quantum science. In fact, it is in 1925 that Schrödinger and Heisenberg found the equations which describe the behavior of atoms and photons at the microscopic level. In fact, this is one of the most important scientific achievements, I think, in all history of humanity. And this has been preceded by discoveries made by such famous people as Planck, Einstein, and Niels Bohr. In fact, the knowledge which has been acquired by this quantum physics has enabled the invention of many contraptions, many instruments which have changed our life in the 20th century. So I recall that briefly, and then I will try to explain that we are now on the verge of a second quantum revolution, which might allow us to have even more impressive instruments in the 21st century. And I will try to explain what we can wait in the future, what we can expect in the future from these discoveries. So let's first recall you some quantum technology of the 20th century. The computers and the smartphones are full of transistors. The transistors came after we understood how electrons propagate in metals and semiconductors, and this is something which belongs to quantum physics. The laser has been made possible once one has understood how atoms interact with photons, and it's an extraordinary source of light which has countless applications. One of them is, of course, the global internet system. You have, at the bottom of the oceans, you have a network of fiber optics cables which propagate light everywhere and which allow all the computers in the world to be connected. And this is, of course, a source of information which has revolutionized our life today. Another example are atomic clocks. Atomic clocks are built on fundamental properties of atoms, which all oscillate at the same frequency. This has been allowed us to build clocks which keep time with unprecedented precision. And these clocks are sent on satellites, and they make the GPS system, which allows us to navigate at the surface of the Earth anywhere with a precision of a few meters. The last example I want to give is magnetic resonance imaging. We have in our bodies a lot of hydrogen atoms which carry small magnetic moments, and these moments are excited by radio frequencies, and the signals they send provide information about the inside of our bodies, and this is a magnetic resonance imaging technique which has revolutionized medical diagnosis, for instance. What I want to say about these discoveries is that before these inventions were made, there was some basic science work which was done by people, by scientists who were not interested in applications. They were motivated by sheer curiosity, and they did not know at all what their discoveries would be useful for. For example, Einstein predicted in 1916 the phenomenon of stimulated emission, the fact that all atoms in amplifying media would contribute together to emit something which became laser light. But it took 45 years between Einstein's idea and the laser, and Einstein, in fact, was dead when the laser was invented. In the same way, Purcell and Bloch were the two young people who in 1945 discovered nuclear magnetic resonance, and they had no idea of the application, and it took 30 years for the development of MRI. So what I want to say is that these inventions have slowly emerged after sometimes in a very surprising way after the initial discovery. And some of this discovery came from the connection between breakthroughs which have been in different areas. For example, for magnetic resonance imaging, you need not only to understand how magnetic moments evolve in atoms, but you need to be able to build huge magnetic fields which didn't exist in 1945, and you need, of course, powerful computers to transform the signal given by the atoms into images. And of course, neither Bloch nor Purcell could know that. I had the luck to meet Edward Purcell in Harvard in the 1980s, and he told me that he was amazed by the applications of his earlier discovery. So why do I say that we are now on the verge of a second quantum revolution? What I want to say is that the first, all what I have said so far, results from the knowledge of the bulk properties of materials made of a huge number of particles. We are working either with laser beams, which have billions of photons, or with atomic samples, for example, the human body, which contains a huge number of particles. Now, what we want to do is to be able to directly observe single atoms, single photons, single artificial atoms also, which behave in a quantum way. And at the microscopic level, very strange phenomena which are hidden in macroscopic systems occur. These phenomena are called state superposition and entanglement. And what we try to do in the second quantum revolution is to be able to harness state superposition and entanglement to achieve tasks which cannot be done if you just work on systems made of a huge number of particles at a time. So I have first to try to explain what I mean by superposition and by entanglement. So what are state superposition and what is entanglement? State superposition means that in a quantum system, a single atom or an electron inside an atom does not have a well-defined position. In fact, it is described by a wave function, which says that it is in fact everywhere at the same time, and that you cannot prescribe to it a well-defined position. The position is acquired when you make a measurement. You have to make it interact with an experimental apparatus, and then it has to collapse at one point or the other. This is true not only for the position, but it is also true inside an atom for the energy of the atom. What quantum physics tells us that an atom can have different energy states which are separated by a well-defined energy difference. It is a quantization, which means that the energy cannot vary continuously, but the atom can be either excited or in a lower state with less energy, but it can also be in a superposition of the two, which means that before a measurement, you cannot tell whether it is excited or not. So this is state superposition. And this story is illustrated by the famous tale of Schrödinger's cat, which we might have heard about, and I will try to summarize this idea here. Schrödinger imagined that a cat was locked inside a box with a single atom. And the single atom is a small box that you can see at the top of this image. The atom is prepared in a state superposition. It is either in the red state or in the blue state. In fact, it is in a superposition of the two. If the atom is excited, nothing happens to the cat. But if the atom comes to the lower state, it means that it has emitted a photon which can trigger a device which will kill the cat. For example, trigger a device which makes a hammer fall on a vial containing a poison, and then the cat is dead. But what happens if the atom is in a superposition of the two states? It means that the cat has to be in a superposition of being alive if the atom has not released the photon, or dead. And in fact, this is what quantum physics predicts. The cat is entangled with the atom in a suspended, so to speak, between life and death. Of course, nobody has ever observed that, and the reason for that is that in a big system like a cat containing a huge number of atoms cannot be isolated from the outside world. There is some information leaking in the environment which causes a phenomenon called decoherence, which kills this quantumness and forces the cat to be either alive or dead. In fact, I mentioned that because this is the investigation of this kind of phenomena and the possibility to control quantum particles at this level of precision, which led to the Nobel Prize that was honored to get in 2012. In fact, if you want to observe this phenomena, you cannot work with big objects. In order to observe directly these strange laws, you must manipulate single, well-isolated quantum systems, which are either atoms or photons or artificial atoms which behave like atoms. And these experiments which open the way to exploitation of quantum logic for practical application. And I will give you a few examples of that. First one is quantum cryptography. Assume that you can prepare two photons in an entangled state. You see the photon on the left is in a superposition of being red and blue, and the same for the photon on the right. But not only that, they're entangled, which means that if the photon on the left is red, the other one has to be red. If the first photon is blue, the other one has to be blue. In fact, these two photons play the role of the Schrödinger cat experiment. One of the photons is like the cat being in two states, and the other one is like the atom. So that's why I made this comparison. But what is interesting here is that the two photons can, once they are prepared in this state, can be flown apart from each other at very large distances. You can send them in an optical fiber, and this very strange correlation, this very strange influence that each photon has on the other is still conserved, which means that if two partners that are often called Alice and Bob share this pair of photons, if Alice makes a measurement and finds its photon red, Bob will find its photon red too, and so on. And this correlation can be used to code information. In fact, you can consider that the red and blue photons code for 0 and 1, which are the binary numbers which are used in all computer science, which means that these two people can share a random sequence of 0 and 1s that nobody else can spy upon. In fact, when they make a measurement, it is as if two dice which were cast at a very long distance from each other always fail on the same face. Einstein could not believe that. That's why he was never accepted what quantum physics tells us. But in fact, he was wrong. All the experiment proves that it is the way it happens. And this phenomenon can be used to code and decode secret keys that nobody can spy upon, because the sequence of 0 and 1 is created when you measure. Before the measurement, the photons which propagate in the fiber are in a superposition of 0 and 1, and no spy, even if he tries to look at, to intercept the signal, will be able to tell. So this is quantum cryptography, and this has been proved, demonstrated by experiments, but you still need to have a lot of work in order to make it useful. In fact, I remind you that between the discovery and the actual practical application, decades have to pass. The second example is quantum information. You see here a string of 54 calcium atoms which are held by electromagnetic forces, making a regular pattern like this one. You can use each atom as a qubit, quantum bit, which code for 0 and 1, and which can be in a superposition of 0 and 1. And each of these qubits is interrogated, manipulated individually by a focused laser beam, and that's why you see them as bright spots. The laser excites them, and they fluoresce. And they can be sent by the laser excitation either in the fluorescing state for 0 or the other state like 1. And what you can do with that is to entangle any of two atoms in this chain by using appropriate laser pulses in a programmable way. And this is the basis of what could be one day a quantum computer. But I'm very careful. We are very far from that now. Here you see 50 atoms, but this kind of physics has triggered a lot of interest. And for example, the European flagship for quantum information, which want to put up to €1 billion into this kind of programs all over Europe. And you have, of course, competing programs in the USA, in India, in Australia, and in China. This was a few years ago. You see here the progress which has been made since then. What you see here is an array of about 6,000 cesium atoms, which can be controlled individually by laser beams, entangled pairwise, and in this way you can perform a huge entanglement in the system. this is a kind of research which is very useful. It's a new tool to simulate quantum matter. These atoms are similar to what you have in a real material, except that they are much further apart from each other. And you can address them individually, which of course you cannot do in a regular piece of matter. So by studying this system, you might discover new phases of matter, and this can be useful if you want, for example, to obtain superconductivity at a high temperature. It's also very promising for quantum metrology and quantum computing. And many startups are now working on that domain. Startups in Europe, like Pascal in France, startup in USA like Quera, which has been founded by researchers at Harvard University. The last example I want to give to you is to come back to the measurement of time and to discuss how quantum physics improves the precision of clocks by increasing continuously the frequency up to clocks which now beat at an optical frequency, a huge frequency, which is the frequency of light. And for that, I come back to the 17th century. The first clock that everybody knows about is just a pendulum clock. The pendulum oscillates at a rate of about 1 second, and this oscillation, by an escape mechanism, makes a needle move on a dial. This was the first scientific clock with which very big discoveries were made. Huygens was really a big scientist of the 17th century, and this clock had a period of about 1 second and an uncertainty of 10 seconds per day. That is it missed about 10 beatings during 100,000 beatings, which is the number of seconds roughly in a day. When quantum physics came about, one has been able to lock a clock on the microwave transition between two atomic energy levels. The frequency is now 10 orders of magnitude higher, about 10 gigahertz instead of 1 hertz, 10 billions of hertz per second. And the precision is increased by the same order of magnitude. Instead of 10 seconds, this clock has an uncertainty of 1 nanosecond, 1 billionth of a second per day, which is the precision required for the GPS to work. But you see 10 orders of magnitude have been won when you go from mechanical clocks to quantum clocks. And this was in the 1970s. Now, 50 years later, we have optical clocks, clocks which are based not on a microwave oscillation, but on an optical oscillation between two energy levels of an atom. And now the uncertainty is 1 femtosecond, which is 10 minus 50. This is 1 millionth of 1 billionth of a second per day. And what I summarize is by saying that these laser clocks, which control single atoms, are 100,000 times more precise than the GPS clock, which itself was 10 billion times more precise than Huygens clock. I think that this shows you all the fantastic progress that science has made in 3 centuries, and the last leap, the last jump in precision was made during the last years. I just show you here a kind of very simplified image of this clock, which is being developed by John E. at Boulder University. You see that you have about 1,000 atoms, which are the blue box that you can see on the picture, about 1,000 atoms which are kept motionless as a crystal, as an optical crystal of atoms. Each atom gives information by being excited with a very precise laser which tries to find out at which frequency the atom is oscillating. And this gives clocks which beat at the frequency that I have written here. It tells you how precise it is. It's 429 terahertz. And terahertz is 10 to the 12 hertz, 1,000th of 1 billion hertz. This is the most precise measurement any made in physics in any field. You have here 15 digits precision. And this gives an uncertainty. If 2 clocks like that had been started at the beginning of the universe 14 billion years ago, they will not depart from each other than 1/20th of a second. So it's a huge precision. And we have to take into account the fact that the time does not elapse at the same rate at the top and at the bottom of the clock because of general relativity effect that I will say in a few minutes about. And this illustrates what Salvador Dali intuitively understood in the 1920s, that clocks become so precise that they are soft clocks. In fact, they give a time which is different at the top and at the bottom of the clock. And we can even think of more precise clocks by entangling the atoms, that is, by making the atoms being related by this entanglement procedure, or by going to larger frequencies. So one does not know what kind of precision we can reach and what we can learn with that. What I want to stress at the last point is a time dilation due to space-time curvature. What Einstein discovered, the general theory of relativity, is that if you have a mass somewhere in space, this mass is changing the shape of the space around. It's introducing a curvature in space, which means that lengths in one direction are slightly reduced and the other direction slightly enhanced, and also the time changes. In fact, the times it goes the clocks are slower near the Earth and beat a little bit faster if you go above. And this has an effect for the GPS. It means that the clocks in the GPS satellites are beating faster, about 38 microseconds per day faster than the clocks on Earth, and you have to take this correction into account for the GPS to be working. Otherwise, the GPS will be off by kilometers. So the GPS is an invention which depends on quantum physics and on general relativity too. You see, here is a picture of these clocks. You see there, you trap atoms at a distance of about 1 centimeter between the top and the bottom of the clock. 1 centimeter makes a difference, and you see that you can see that the atoms do not respond at the same frequency at the bottom and at the top of the clock. So what can be the use of that? What you can do if you move this clock at the surface of the Earth, it will beat at a different rate if you have some inhomogeneities of masses below. For example, if you have some water underground, you will detect this water by the fact that the clock will change its rate. If you have an earthquake which is starting to move the Earth plate underground, the precursors of the earthquake can be detected by such very sensitive clocks. So it's a very useful tool to measure the form, the exact shape of the Earth in geophysical studies. So I just summarized here to conclude the 4 directions of this quantum information revolution. The one is, first is quantum metrology, which I just described, the fact that you can use quantum properties to make very precise measurements of gravitational fields, of electric and magnetic fields, and it can be very useful. The second is quantum communication, and I already discussed it. The third is quantum simulation, and I also alluded to it. You can build, like you do a Lego game, you can put atoms at well-defined position and study their quantum properties, and it can be useful to synthesize new materials. And of course, the last step is a quantum computer, and there are several candidates for that, and there is a lot of work in this respect, but I will say a few caution words in the end. So how can we ensure the success of this research? The first point is that you have to keep a strong basic research, and I always insist upon that, because you cannot know which fundamental discovery will be useful. By definition, you need to acquire knowledge, and sometimes you have surprises. This knowledge will show you what you can do, but before basic research is done, there is no way that you will have useful application. You must also facilitate multidisciplinary research, because you need, of course, the expertise not only of physicists, but also of mathematicians to find the right algorithm to work on this machine. You need also chemists for quantum simulation. You need material scientists, geologists, and biologists. And what you can expect, for example, is to have very sensitive probes for Earth geodesic studies and for application in biophysics. You can also expect very interesting results for quantum simulation to synthesize new materials and new molecules, for example, for therapeutic usage for new drugs. A word of caution. We have to avoid hype and overselling. Everybody, the big companies like Google and Microsoft, keep talking about the quantum computer as if it was for tomorrow. In fact, there is a lot of work which remains to be done, and I am myself very doubtful about the fact that we will have a machine like the one that these people are envisioning. They are promising a quantum computer in the near future, and this future is receding all the time, and it had started around 60 years ago. So there will be certainly very interesting results, but nobody can know exactly what it will be. What I want to say is that the instruments which will be invented in this century might surprise us as much as lasers would have surprised Einstein a century ago. And this is the beauty of research. You cannot predict what will happen. Now, I have a last slide that I would like to show because I think that basic research is important, not only because it might have application, but it is useful even if it is useless. And I think because the basic knowledge is an essential pursuit of mankind, especially necessary to preserve the values of civilization in dark and dangerous times. This was mentioned already by Abraham Flexner. Abraham Flexner was the founder and the first president of the Princeton Institute for Advanced Studies. He's the guy who invited Einstein, von Neumann, Gödel, and other luminaries who had to flee Europe in the 1930s. And he wrote a book which expressed exactly what I have said, and he gave it the provocative title, The Usefulness of Useless Knowledge. And I just quote here the first sentence of the book. Is it not a curious fact that in a world steeped in irrational hatreds which threaten civilization itself, men and women, old and young, detach themselves wholly or partly from the angry current of daily life to devote themselves to the cultivation of beauty, to the extension of knowledge, to the cure of disease, to the amelioration of suffering, just as though fanatics were not simultaneously engaged in spreading pain, ugliness, and suffering. This was written in 1939, and I think we have to reflect about that. We scientists are very much worried about what's happening now with the anti-scientific movements that we see everywhere, with the attacks on science. I think it is very dangerous. It comes from the fact that I think that people are threatened by science. A lot of scientific discoveries are destroying some industries and creating new ones. I think artificial intelligence is an example of that. And the people are afraid to be left on the side of the road, so develop resentment against science, and I think it is very dangerous because only science can solve the problems which are facing the planet today. So we, as scientists, we work as a siege society, people who are under the pressure of finding solution and at the same time to have to respond to irrational attacks. And I think Flexner understood that very well in the 1930s, and we have to reflect about that. Thank you very much for your attention.